Oh, welcome to lecture or week 12 of the Internet Seminar. And the topic today is square roots of elliptic operators. And as a start, I want to write down the main result, the main theorem that we will prove more or less in the remaining course. So today I will give the theorem and comment a little bit and make a first reduction step. In chapter 12 we will do a first reduction step, and then lecture 13 and 14 will be dedicated more or less to the proof of this theorem, which is the solution of the Kato conjecture. So somehow the grand finale of this year's ISAM. And so what does this say? Take a divergence form operator, elliptic operator in divergence form, such as we have considered it several times during the lectures. And as I said, as I said last week, for the rest of the Internet Seminar we will not treat boundary conditions, so we are always on the whole space Rn. And what the Kato conjecture says is that the domain of the square root of L is exactly the form domain of the corresponding form, so it's exactly H1, with equivalence of norms and even equivalence of the homogeneous part of the norms. So for every u in H1, if you look at the norm of square root of L applied to u in L2, this is an equivalent norm with the gradient of u measured in L2 for all u in H1. So in particular, this gives you that the H1 norm is equivalent to the graph norm of the square root of L, but it's even better, it's even the higher order terms of both norms alone are equivalent. Okay, so this is the Kato conjecture, the Kato property of divergence form operators, which has as we already saw in earlier lectures, it has a very long history going back to the 60s of last century. It was solved in this version on Rn in the fundamental work of O'Shea, Hoffman, Lacey, McIntosh, and Chamichian 2002. And there were many developments up to this result, and after this result there were also many follow-ups, many more developments following generalizations, applications of this lecture, of this result, and it's completely hopeless to name them all or to give full credits for the history of the result and for what came after. In the lecture notes there is a very small personal collection of some of these results on some timeline, which you can look at. But yeah, it's far from being a complete thing or something. This is a huge story. And as I already said, the aim of today's lecture or of this week's lectures is first to show you why the square root is the critical thing, so why this is a non-trivial and important result, and then to do a reduction, the first reduction step, and to show that this can be proved by proving the right square function estimate, which brings us back to the topics and the techniques we did during the last weeks. Okay, but the first and somehow the main topic today is the subsection on why square roots are critical. And let me do a small drawing for this, which somehow summarizes some things that we already saw in the lectures and that we will see today. So let's look at the fractional powers of L, so L to the alpha. So here is alpha. Alpha being 1 corresponds to the operator L. Okay, alpha being 0, L to the 0, somehow the identity. Here is the square root, and here are the fractional powers. Okay, and what have we seen so far? We've seen in chapter 8 that from 0 to 1/2 everything is nice. Or let's start with the bad result that we had for the full operator. So for the full operator, we've seen that the domain of L, which in a first view, very naively, one could say, okay, this is an operator of second order. So somehow, if we look at this operator in L2, the domain should be H2. Should be 2 times weakly differentiable functions over L2. And this is completely false. We've even seen an example that it might happen that the intersection of the domain of L and this space H2 is just a 0 function. So it drastically is false. This was exercise 4.6. So this exercise 4.6 was in 1 dimension, but as soon as one knows how to do it, it's no problem to do it in arbitrary dimensions. So the domain of L is far from being H2, but we also had positive results. So if you look at small powers of L, then everything is all right. So the domain of L to the alpha then is H2 alpha. This was corollary 816. So up to 1/2, for alpha strictly less than 1/2, the domains behave as one would expect. So the domain of L to the alpha, as one would expect, if the domain of L is all of H2, then one would expect that the domains somehow increase linearly in alpha. Okay, and this works fine up to 1/2. We've seen that in a very special case, this behavior even stays true up to 1/2. So the domain of L of the square root of L indeed is H1 if A is a Hermitian matrix. So if the operator L is self-adjoint. This was corollary 613. So up to 1/2 for some matrices, up to 1/2, strictly less than 1/2 for every divergence from operator, in 1/2 for some very special matrices. And what I will show today is that for greater 1/2, nothing more is to expect. So here everything is fine. Up there things go completely wrong. So somewhere in between 1/2 and 1, the catastrophe must happen. The question is, where does it happen? And the answer is, it happens not at 1/2. So this proposition tells you, if once we've proved it, this proposition tells you that 1/2 is still okay for every divergence from operator, regardless of what the coefficients A are. But what I will show today is that exactly here is the cut. And for alpha bigger 1/2, there is nothing more to expect. So there will be a proposition 12.2 today. So proposition 12.2 tells you that there is possibly no improvement at all going for alpha greater than 1/2. So, and what is this proposition 12.2? We'll show exactly that. For alpha greater 1/2, things can break down. And it's even nicer. I will not claim that for every alpha greater than 1/2, there is an elliptic operator where things break down. But even uniformly, I will show there is an elliptic operator. There is a coefficient matrix A where things break down for every alpha greater 1/2. So there's one operator that already makes things destroys things. So proposition 12.2 says there is an elliptic operator L in divergence form. Again in R, so for n equal 1, but this is for simplicity of exposition. Once you have the result, it's not that complicated to generalize to higher dimensions. It's just more writing and more indices, but it's the same idea. Okay, so there is an elliptic operator in divergence from L on R, and there is a function U in the domain of this operator such that for every epsilon positive, U is not in H1 plus epsilon. So the square root has domain H1, still to be proved, but the domain of L is not contained in any Sobolev space of higher regularity than H1. So there is one elliptic operator which makes all this red line break down. And the task for today is to construct this operator. I already said this, so remark 12.3 that we choose n equal 1 here is only for simplicity. And there is an exercise in the end, so exercise 12.3, which invites you to check this and to generalize the idea to higher dimensions. Once more? Yes. It's not in there. Thank you. That's the crucial thing. Yeah? So there is a function in the domain, even in the domain of L, that is in none of these Sobolev spaces. Okay. So what this in particular means, I should write this down. So proposition 12.2 means in particular that for every alpha between 1/2 and 1, the domain of L to the alpha is not contained in H2 alpha of R. So this is what the drawing is about. So the result like this one for higher fractional powers of L is out of reach. So as soon as alpha is greater than 1/2, you will not get a result like that. Okay, so this is the reason why square roots are critical. So the square root is the limiting case, and the question is, does it work out or not? And the answer is yes, but this is some hard work and a very powerful result. Okay, so, but let's first show that things go wrong if we are above the square root. And in order to prove this proposition, we will first need two lemmas. And for these, it's good to recall some stuff from earlier lectures, so from lecture 4. First thing is how, in the first place, were these fractional Sobolev spaces defined. So H alpha of Rn was just defined as the domain of the corresponding power of the negative Laplace operator. for the negative Laplace operator. Here everything is nice, so the domain of the negative Laplace operator is in fact L2. And you have equality of all these domains with the corresponding fractional Sobolev spaces just by definition. So the fraction, they were just defined like that. And then we will need proposition 413, which somehow characterize the space in form of its norm, of a equivalent norm, so-called Sobolev-Slobodetsky norm. So if you have an alpha between 0 and 1, then U is in H alpha of Rn if and only if U is an L2 function and the following norm is finite, or semi-norm is finite. So this was denoted by this brackets U alpha 2 and is given as the double integral over Rn and Rn, this difference between U of x minus U of y squared divided by x minus y to the 2 alpha, so some, and then integrate with respect to the measure dx dy over x minus y to the n, and this to the 1/2. And if this is finite, if and only if U is an L2 and this quantity is finite, then U was in H alpha, and this quantity also gives you an equivalent norm. So the norm L2 of Rn squared plus this semi-norm squared to the 1/2. This is an equivalent norm to the H alpha norm. Okay. So this is proposition 413. We will need this. Okay. And then the first lemma that we will need to prove this negative result about the powers above 1/2 is some lifting property for the Sobolev spaces. So we have to look at the Sobolev space H1 plus epsilon, so a little bit more than one Sobolev regularity, and some obvious question is, can I describe being in H1 plus epsilon by saying, okay, it must be in H1 and the gradient still must have epsilon regularity. So is this the same as saying, so being in H1 plus epsilon, is this the same as saying U is in H1 and the gradient of U is in H epsilon? And the answer is yes. And this is this lemma. So for every epsilon between 0 and 1, the space H1 plus epsilon of Rn is the same as the set of all U in H1 of Rn such that the gradient of U is in H epsilon. In Rn to the n, yeah? The gradient is a vector. So. And so what in fact we will prove is also some equivalence of norms. So the norm on H1 epsilon, H1 plus epsilon, is equivalent to the norm that you get by putting these two things together. So this is equivalent to the norm on H1 plus the H epsilon norm of the gradient. So squared 1/2. Okay, and in fact it's this what we will prove. Once you've proved this norm equivalence, you know, yeah, if your function is an H1 plus epsilon, then these two are finite, and the other way around, if these two are finite, then this is finite. Okay. And the the main trick to get this is, how are all these norms defined? They are defined by the mapping properties of the Laplace operator on Rn, and the mapping properties of the Laplace operator on Rn can all be described by Fourier transform by multiplication operators on Rn by Fourier transform, and this is what we will use. So we will use the results that we had in lecture 4, which allow us to rewrite all these norms on the Fourier side. So once you have a function that is in L2, then you know that the Fourier transform of this function also is in L2. And by results of lecture 4, we get characterizations of all the spaces that are of interest to us. So U is in H1 plus epsilon of Rn if and only if the function modulus of psi 1 plus epsilon U hat of psi is an L2 function. So it's in H1 plus epsilon if you multiply by a polynomial growth with growth 1 plus epsilon, you are still in L2 on the Fourier side. Same thing for H1. So U is in H1 of Rn if and only if modulus of psi times U hat is an L2 function. And the gradient of U is in H epsilon. This is also something we need if and only if modulus of psi to the epsilon, modulus of psi multiplied with U hat is in L2. Psi multiplied with U hat is more or less the gradient. And if you multiply this again with psi to the epsilon, this means the gradient is in H epsilon. Okay. And using these characterizations, we can now prove the equivalence of norms. Okay. I start with the H1 plus epsilon norm, and I write a squared to avoid writing all these square roots. Okay, this is equivalent to the norm of U in L2 squared plus the derivative part. So as written up there, modulus of psi to the 1 plus epsilon times U hat of psi. This function must be in L2. Oh, I will not write all these Rn's now. Okay. So this is the H1 plus epsilon norm. It's equivalent to the H1 plus epsilon norm of U. Okay. This is a scalar thing, so you can put these into one absolute value, or you can split this to. So this is the norm of U in L2 squared. Now I split this modulus of psi to the 1 plus epsilon to a modulus of psi to the epsilon times modulus of psi modulus of U hat. So like that. And this now gives us, see the last line up there. So this is again equivalent. No, I will only use, this is less or equal. So here I add something to make this the H1 norm of U. So I add the L2 norm, the weak derivative of U. And here I add the L2 norm of U. And then this is the H epsilon norm of the gradient of U. It's less or equal than this thing. You have to add the L2 norm of U. Okay, and this already gives the first part of the equivalence of norms. Yeah? So this norm is equivalent to that norm. Is less or equal that norm. That's the first part of the equivalence. Now we have to go back. Yeah? We have to continue estimating from above and ending up there. Okay, so let's write out this H1 norm again. So this is u in the L2 norm squared plus modulus of psi times modulus of u hat in the L2 norm. This is this H1 norm here. And we from here there is a so there is a L2 norm of the gradient of u. This gives one more of these. The L2 norm of the gradient of u is exactly this one, so I have a 2 here. And then there is the L2 norm of psi to the epsilon gradient of u. So this thing. Okay, so one of these comes from here, one of these comes from here. And now what we will do is, let's first forget the 2. Then what I will use is that modulus of psi is less or equal than 1 plus modulus of psi to the 1 plus epsilon for all psi. So for large psi, this is clear because 1 plus epsilon is a bigger exponent than 1. And for small psi, let's say psi less than 1, we can just estimate by 1. Okay. So I can always estimate modulus of psi by this. And if you put this in here, what you get is the L2 norm of u squared plus, so this gives two norms. This gives the L2 norm of u hat from the 1 plus the L2 norm of modulus of psi to the 1 plus epsilon u hat. But this is the same as this one. So we have a 2 here. Okay, these two are the same, so this is less or equal than u in the L2 norm squared plus modulus of 1 plus epsilon modulus of psi to the 1 plus epsilon u hat of psi in the L2 norm squared. And this is nothing else, or this is equivalent to the h1 plus epsilon norm of u squared. Okay, so somehow it's all doing Fourier transforms and estimating norms, and the main trick is this one. And then you have the same here, and you have all the equivalence of norm. This norm is equivalent to that norm, and this gives you the lemma. Okay. So that's the first technical thing, which is somehow plausible, that you can describe h1 plus epsilon by saying the function is h1 and the gradient is h epsilon. Now we are on safe ground. This works. So we can start to think about how to construct such a bad operator L. So the aim is to construct a bad operator L, so to have bad coefficients that somehow destroy regularity. And the trick is, again, as we had it already in lecture 4, to have coefficients that are discontinuous and that oscillate very much and that jump up and down all the time. So we will take again the coefficients of the form 1 plus the characteristic function of some awful set, and somehow the construction of this awful set. This is what we will do in Lemma 12.5. So I claim there exists some set E subset of the closed interval 0, 1, open subset of the closed interval 0, 1, such that the following thing holds for every epsilon between 0 and 1, the double integral 0, 1, 0, 1, characteristic function of e at x minus characteristic function of e at y squared divided by x minus y to the 2 epsilon integrated with respect to dx dy over x minus y to the n, that this is infinite for every epsilon. And if you now look back to the proposition 413 that I recalled in the beginning, then you see why this quantity is of interest. This is exactly this Slobodetsky semi-norm for this characteristic function e. So what this means in particular is that the function e, that the characteristic function of e is in no Sobolev space for every epsilon greater than 0. So this is a characteristic function of a set that has no weak regularity for no epsilon positive. Because if it would be in H epsilon, then somehow this property is finite. Okay, and this function e will then be used later to define our coefficients of the bad operator L. Okay, but first the question is, why does such a nasty set exist? So first thing to note is why this in particular holds, and this is just because if as E is bounded and open, so E is in the interval 0, 1 and open, this means that the characteristic function of E is an L2 function. It's measurable because it's a measurable set, and it's L2 because it's bounded on a bounded set. Oh, guys, with support in a bounded set and bounded. So we know that this is an L2 function. And then if you look back at 413, this tells you if you have an L2 function, this is in H alpha if and only if the Sobolev-Slobodetsky semi-norm is finite. It's not finite, so this function is not in H alpha, H epsilon. So the in particular part follows from 413. Okay, so how do we now get this awful set E? And the one way to construct it is to choose a particularly chosen sequence AJ. I will give some of its properties that we need in the beginning, and some of the properties that we need will get clear at the end of the proof. But let's, for the moment, take any decreasing sequence of numbers between 0 and 1, such that the series over AJ, such that this series is convergent and the value of the series is 1. So up to now there is still much choice how to choose this sequence AJ, and then we will need the partial sums of this series. I will call them SK. So SK is J going from 1 to K AJ. It's the partial sums for K in the natural numbers including 0. It's important to include 0 here. I will need the S0 in a moment. S0 is a sum, is an empty sum, so S0 is 0. Okay. So these are the partial sums of our sequence, of our series, and using these partial sums, I can just write down E. So what we will do, here is 0, there is 1. So 0 is S0. And then this AJ is a sequence of positive numbers. So the partial sums are increasing. They are increasing to 1. So somehow here is the first partial sum, the second partial sum is 4, S5, S6, and so on and so on. So these are the partial sums. And what is my set? I just take every second interval that is given by this decomposition that are given by the partial sums. So I take the first, this interval here belongs to E. I do not take these numbers. I take these numbers between S2 and S3, the numbers between S4 and S5, S6 and S7, and so on. So this is my set E. So my set E is the union for k going from 0 to infinity of all open intervals that you get if you start with a partial sum with an even index, so S2k to S2k plus 1. This is a union of open sets, so it's open. It's a subset of 0, 1. It's just taking every second interval between these partial sums of our series. Okay. And I claim this set E does the trick. If we choose the sequence AJ the right way. And there is so what do we have to prove? We have to prove that choosing AJ in the right way, all these terms here are finite for every epsilon positive, or epsilon between 0 and 1. And as one can imagine, the big epsilons are not the issue. Problem about this, or the difficult part is epsilon close to 0. So let's first deal with the easy epsilons, so epsilon greater than 1/2. And for epsilon greater than 1/2, to show that this is infinite is easy. So what do we have to look at? We have this double integral 0, 1, 0, 1 of the difference between the characteristic function in x minus the characteristic function in y, divided by x minus y to the 2 epsilon, and integrated with respect to this measure dx of dy over x minus y to the n. N is here 1. Okay. And we want to show that this is finite, so it suffices to estimate from below. And we do a rather crude estimate. We have to look at all pairs of x and y. For x and y both between 0 and 1, the integrands are all positive. So if I restrict to x or y being from 0 to S1 and x being from the interval S1 to S2, so I take the y here, I take the x here. This is less, because here there's much more integrated than only these two intervals. But this already suffices. So reduce this integral by just taking smaller intervals to integrate. Then the good thing is that if you know that your y is between 0 and S1 and your x is between S1 and S2, then you know that this number here is 0 and this number here is 1, because y belongs to E and x does not belong to E. So this difference is 1. And then you have 1 over x minus y to the 2 epsilon plus 1 dx dy. And you even know, okay, the y is so the x is between S1. The x is larger than y, so you can even take out the absolute value and do normal parentheses. Okay, and now you can just integrate. It's just So at least the inner integral can be calculated. So this is primitive of this function is minus 1 over 2 epsilon 1 over x minus y to the 2 epsilon x going from S1 to S2 dy. So this gives you integral from 0 to S1, x being S1, 1 over 2 epsilon is everywhere. 0 to S1, 1 over S1 minus y to the 2 epsilon dy minus integral from 0 to S1, 1 over S2 minus epsilon to the 2 epsilon dy. And now if you look at these two integrals, the second one is finite, because S2 is strictly larger than S1. You integrate from 0 to S1 the function 1 over S2 minus epsilon, which is a nice continuous function here. So this is finite. And here you have an integral up to the singularity. So from 0 to S1, 1 over S1 minus y. And since epsilon is greater than 1/2, this exponent is greater than 1. So this is a non-convergent integral. So this is infinity. This doesn't help. So this is infinity. So for not too surprising for large epsilon, this function is not in H epsilon. But the more interesting case is the case where epsilon is between 0 and 1/2. And you see, for the first case, I even didn't need that my sequence is very sophisticated. I just needed that it has one jump. I just needed that there is an interval where it's 0 and an interval where it's 1 that are close together. So, but now we have to carefully look into how this sequence AJ behaves. Okay, but the main idea is the same thing. We just are a little bit more cautious. So we start again with our double integral, 0 to 1, 0 to 1. The difference of the two characteristic functions squared divided by x minus y to the 2 epsilon plus 1 dx dy. And we again want to bound from below. And the idea is again not to consider all interactions between x and y, but only interactions between x and y where we know that this difference is 1. And what we will do is we will only look at always at two consecutive intervals. So somehow here we only looked at the first two intervals. Now we will do a sum over all the intervals, but always saying, okay, we take y in this interval and x there, plus y here and x there, y here and x there, y here and so we again throw away many of the interactions of y and x. This is okay. This makes things smaller, and we keep interactions of y and x in two consecutive intervals where y belongs to E and x does not belong to E. So this gives us a sum going from 0 to infinity, going along the intervals, and then we integrate the y from S2k to S2k plus 1. So this is exactly one of the intervals that belongs to E. And we integrate the x from S2k plus 1 to S2k plus 2. So this is the next interval that does not belong to E. And then if we do this, we know that this difference is again 1. Because now y it belongs to E and x does not belong to E. 1 over x minus y to the 2 epsilon plus 1 dx dy. Okay. Next step is to use that our sequence is decreasing. What I want to do is I somehow want to force that these two integrals integrate over intervals that are of the same length. And I will do this in the following way. So this second interval, this you can rewrite as going from s2k plus 1 to s2k plus 1 plus a2k plus 2, because the 2k plus 2 partial sum is the 2k plus 1 partial sum plus the summed with the number 2k plus 2. This is just rewriting this partial sum. And now I know that these two are more than 2k plus 2 apart because the sequence aj is decreasing. So if I integrate here up to s2k minus 1, but here only up to s2k minus 1 minus a2k plus 2, this number here is greater or equal than s2k, because a2k plus 2 is less than a2k plus 1. Okay, and then we integrate the same thing. X minus y to the 2 epsilon plus 1 dx dy. And once we are here, we can now estimate rather rudely by saying, okay, how far are, so I want to estimate this from below. So to make this smaller, I have to make the denominator bigger. So how far are x and y at most apart? How far are they at most apart? X might be here and y might be here. And both intervals are of length 8 take 2k plus 2. So this is greater or equal 1 over 2a take a 2k plus 2 to the 2 epsilon plus 1. So the whole thing so if I do this estimation, I have the sum k going from 0 to infinity. Then I have this denominator 2a 2k plus 2 to the 2 epsilon plus 1. And if I take this out of the integrals, this is just integrals over the constant 1 function. So I just have the length of the intervals. The length of the intervals is a2k plus 2 and a2k plus 2. So this gives 2a2k plus 2. So this is the two lengths of the intervals, which are multiplicative. Okay. So the two lengths of the intervals give these, and this is the constant by which I estimated. Now you can do some cancelling here. So this gives 2 to the minus 1 minus 2 epsilon, this 2, times the sum k going from 0 to infinity, a2k plus 2 to the 2 minus 1, so this is 1 minus 2 epsilon. Okay. So what do we need for our sequence aj? So we need for a sequence, let's collect, ag must be decreasing. It must be contained in 0, 1. We need that the sum of the whole sequence is 1. And we need that if you sum the only the part of the sequence with pair indices, and you take it to the power 1 over 2 minus epsilon, this has to diverge. And it has to diverge, it's to the alpha, it has to diverge for all alpha in 0, 1. So alpha is somehow 1 plus 1 minus 2 epsilon. This has to diverge because we want to have this to be infinity. So we need a sequence that is summable to 1, but if you add a little exponent, it must have an infinite series. And now somehow this is a recurring theme of this internet seminar. It's good to recall the so-called Bertrand series. Which is this sort of harmonic series with an additional logarithmic term. So if you take a harmonic series and you add the square of a logarithm in the denominator, then this is a convergent series. So 1 over j plus e gives you the harmonic series. So 1 over sum over 1 over g is a harmonic series, so it's divergent. But if you add a square of a logarithm here, this gives a convergent series, which goes to which has some value, which is not further important. I will call it c. And now take this aj to be 1 over c to make it converge to 1. So make the series converge to 1. G plus e square of g plus e. So this gives you a sequence that is summable, and the value of the series is 1. That's why we normalized with c. And if you add an arbitrary small power to it, the logarithm will no longer help that this one is that this series over j to the alpha for alpha less than 1 is divergent. So then you get a divergent series. So this is exactly what you need here. Okay, so this is the right choice of aj. Yeah, there are several others, but what you need is a series that is convergent, and as soon as you take the summons to some little power, it gets divergent. And this is one of these examples. Okay. Okay. These sort of sets are more here we use them just to get the right elliptic operator, but they are also known in the geometric measure theory as nice counterexamples to many things. And so someone from geometric measure theory would be saying that what we've proved now is that this set has infinite epsilon fractional parameter. So that's the notion there. But it's nice to see that something like this is possible. And what I want to show you now is that using this, we will really get an operator L that does what I said, that is a counterexample for every alpha greater than 1/2 at the same time. Okay, I think I clean a little bit the backboard. And probably I continue then because there is 10 or 15 minutes left. The lecture 12 is a rather short one. Okay. So, we are left to do the proof of our proposition 12.2. And we've done the main steps, so we've found this weird set E. And I will first comment perhaps on the in particular part in Remark 12.3. This is again a more or less easy consequent of this proposition 12.2. So take some u in the domain of L. So suppose we've proved proposition 12.2. So this means there is a u in the domain of L that is not in any Sobolev space with regularity greater than 0. So I can take a u in the I take an alpha between 1/2 and 1, and I take a u in the domain of L that is not in H 2 alpha. This is possible by proposition 12.2 because this tells me there is a u in the domain of L that is not in H1 plus epsilon, so for any epsilon. So since alpha is greater than 1/2, 2 alpha is greater than 1, so I find such a u. Now that is what we will prove in proposition 12.2, but for the moment, suppose that this is true. Then this function u is in the domain of L, so in particular is in the domain of L to the alpha, because alpha is less than 1 and the fractional powers are nested. So this is a function in the domain of L of alpha that is not in H2 alpha. And this is what the in particular part says. In particular command in Remark 12.3 says for every alpha positive greater than 1/2, the domain of L to the alpha is not included in this space. Okay, and now let's prove that such a u exists, or prove that such a bad behavior of the fractional power domains for alpha greater 1/2 is possible for an elliptic operator with the indivergence form. And I already told you what is the idea. We take the set from lemma 12.5, and then we look at the coefficient function that is given by 1 plus the characteristic function of this set E. So this operator is the Laplace operator plus some perturbation, and the perturbation is only in the interval 0, 1, and in the interval 0, 1 the coefficients are jumping wildly between 1 and 2. So the coefficient is 2 on the set E, and everywhere else they are 1. So, and take this coefficient and using this coefficient define the corresponding divergence form operator in 1 dimensions. So 1 minus L is minus derivative of 8 times the derivative of the function u. And this is a nice elliptic operator because our coefficients are always between 1 and 2. So L is elliptic, and so the corresponding form is bounded and it's elliptic, and we find a nice elliptic operator in divergence form like that. And now we still have to find this function u, and the ways to construct this function u is the following. Take the primitive of 1 over a. So define the function v of x as the integral from 0 to x over 1 over a of y dy. So v is just the primitive of 1 over a. This is a nicely defined function. 1 over a is between 1 and 2, so 1 over a is between 1/2 and 1. No problem to do the 1 over a, and then you integrate from 0 to x. This gives a nice continuous function. It's not only continuous, it is even absolutely continuous. So as long as you look at it on a bounded interval, it's a nice h1 thing. So v has a nice weak derivative, and the weak derivative is 1 over a. So this is weakly, and this was shown in Theorem 312. Okay, so v is weakly differentiable, and the derivative is 1 over a. So the problem is that this function v is not really a nice Sobolev function because it has no decay at infinity. It's even. This is an integral over something between 1/2 and 1, so this gets large. But we are not interested in what happens for x equals minus 250 and plus 2 million. We're interested in what happens between 0 and 1, because between 0 and 1 our operator is nasty. Outside it's just Laplace operator. So this is an artificial problem. Let's cut it off. So take the right cutoff function, some CC infinity function on R that is 1 on our interval of interest 0, 1, and then goes down. And then now our function u is not this v, but is v times eta. So we just cut off the problems of v. But we are not interested in what happens outside of 0, 1. Okay, on 0, 1 we have it 1, so here it doesn't destroy anything. Okay, so let's look what this function u, what the properties are. I claim it's a continuous function. Eta is nice, but v is continuous because v is a primitive of something. Okay, so this is a continuous function. I claim u is also weakly differentiable. Okay, it's something weakly differential times some CC infinity function. So weakly, the derivative is given by the product rule. So this is just the product rule, v prime eta plus v eta prime. But we know v prime. So this is eta prime v. V prime is 1 over a, so this is eta over a. So, and now I claim u is in h1. And this is because v has a nice weak derivative, but is not L2. By multiplying with eta, we make it L2. So this is in h1 since u and u prime are both bounded. And you have bounded support. Bounded support given by eta, and that u and u prime are bounded. U is v times eta. V is a continuous function, and on the support of eta, this is bounded. And u prime, okay, eta prime is bound. This is again v times something with compact support. So this is bounded. Eta is bounded. And 1 over a is bounded. Okay. So, and what we want to show is this function u is the function we are searching for. So I claim this function u is in the domain of L, but for all epsilon positive, u is not in h1 plus epsilon. And once we have this, we've proved our proposition 12 too. Okay. And what we have to show to get this, or no, we have to prove two things. So we have to prove that U is in the domain and that U is not in any such space. Okay, so to prove that U is in the domain, we show that A applied to U prime is in H1. Why does this suffice? Yeah, because if A U prime is in H1, you can do another derivative of this one, and the derivative of A U prime is just LU. Then LU is in L2. So this means that U is in the domain. So once you have this gives you U in the domain. This was exercise 4.6. Okay. So what we have to make sure is that A times U prime is in L2. Is in H1. A times U prime is in H1. So we have to have one more weak derivative in L2 here. And why is this? Okay. If you want to calculate A U prime, you have to take this times A and then you have to differentiate. So at some point we will have to look what is A eta prime. So if you multiply by A here, you have to look at what is A eta prime. And now there are two cases. Yeah? If you are on 0, 1, or if you are outside of 0, 1. What happens in 0, 1? Now in 0, 1, this function is awful. But this function eta is constantly 1, so if you differentiate, this is 0. Something awful times 0 is 0. It's nice, so we do not have to bother about what the A is on 0, 1. That's just 0. And what happens outside of 0, 1? Outside of 0, 1, the A is just 1. So outside of 0, 1, this is eta prime. This can be written more shortly. This is eta prime. Yeah, because on 0, 1, eta prime is 0, and outside of 0, 1, the eta prime is eta prime. So A eta prime is just eta prime. And this is the main observation to do to make the things work. So what is AU prime? AU prime is A eta prime V. So this is this line here, A eta prime V plus A eta over A, so plus eta. So this is this one. So A eta prime is just eta prime. So this is eta prime V plus eta. And what is our aim? Our aim is to show that this function is in H1. Yeah, but this function is V, which is V multiplied with something CC infinity. So this is H1 plus something CC infinity, which is really H1. So this implies that this is H1. And you can even calculate the derivative. So what is AU prime? So what is LU? So LU is, so you have to differentiate this. This is eta double prime V plus eta prime V prime plus eta prime. Notice the nice thing is we do not have to differentiate V prime. We do not have to differentiate V prime, because that would be a problem. You can nicely differentiate V, but never dare to differentiate V prime, because V prime is 1 over A and A is jumping like mad. Yeah? So the main point is that somehow the V prime here is cancelled out. And like this, it's possible to differentiate again the AU prime. Okay. So why do we have to calculate this? Because this was a bit premature. This has a weak derivative. No, it's H1. It's H1, yeah, because this is L2. This is L2 because, okay, CC infinity, something continuous times CC infinity, no, not continuous, but something bounded times CC infinity, something bounded times CC infinity. Okay. So what this shows us is that AU prime is in H1, so we have that U is in domain. What is missing is that U is not better than H1. It's in H1, but it's not better than H1. So check that U is not in H1 plus epsilon for any epsilon. And now this is evidently where the special form of our set E comes into play. So what is U prime? And we will use the lifting property that I showed earlier. So we will use that U not being in H1 plus epsilon means that the gradient of U, so U prime, is not in H epsilon. And we saw that this is equivalent, U being in H1 plus epsilon and U being in H1 and the gradient of U not being in H epsilon. So let's check that U prime is not in H epsilon. So what is U prime? Yeah, U prime is V prime times eta plus eta prime V, but we are only interested on the interval 0, 1. So on the interval 0, 1, U prime is easier because on the interval 0, 1, this is just 1, so this is V prime. So this is 1 over A. Now you see the 1 over A is a nasty function. So things are nice. So what is this 1 over A? A is 1 if the point is in E and 2 otherwise. No, 2 when point is in E and 1 otherwise. So 1 over A is 1/2 when the point is in E and 1 otherwise. So this is 1 minus 1/2 characteristic function of E. So this is 1 if the point is not in E, and it's 1/2 the point is in E. Okay. So let's check that this function U prime is not in H epsilon of the interval 0, 1. So look at integral 0, 1 to 0, 1. U prime of x minus U prime of y squared divided by x minus y to the 2 epsilon integrated with respect to the measure dx dy over x minus y modulus to the n. N is 1 here. So this is the thing that we have to check for the Sobolev-Slobodetsky seminorm. If we show that this is infinite, then this function is not in H1 on the interval 0, 1. But we want to show that it's not in H epsilon of R. So in fact, you have to have this integral over all the stuff. But if this is already infinite, the whole thing is infinite. Okay, so the interesting things happen between 0 and 1. Okay, so we know what U prime is. U prime is this stuff here. So this is integral 0, 1, integral 0, 1. Okay, if you take this in x minus this in y, the two ones cancel. And what you get is 1/2 times the characteristic function of E in x minus the characteristic function of E in y squared. Okay, and the squared gives you here 1/4 over x minus y to the 2 epsilon dx dy over x minus y in modulus. Okay. So this was using that we know how the U prime looks like. And this is something we've already seen. Now you see the construction of E was made explicitly to control, or to even to explicitly not control this term here. So this is 1/4 times the thing that we showed earlier is infinite for every epsilon positive. So the E was constructed to make this work. Okay, so, and now invoking 413, recalled earlier, this means U is not, U prime is not in H epsilon of R. And then taking 12.4, so the lifting property for the Sobolev spaces, this means that U is not in H1 plus epsilon. Because we know U is in L2, so U is in H1, we know that. And once you know that U is in H1 and you know the derivative is not in H epsilon, then U is not in H1 plus epsilon. Okay. So this proves proposition 12.2. And we've seen for fractional powers below 1/2, everything is nice for every operator. There is no hope to get a general result for any alpha greater than 1/2, because there's even one operator who destroys it for all alpha greater than 1/2. And what remains is the critical point in between, for alpha equal 1/2. What is, and the question whether the equality of the domain of the fractional power to the corresponding Sobolev space stays true for all divergence from elliptic divergence from operators. This is the Kato conjecture, and this is the critical case. It's the borderline case. That's what we saw today, and on Wednesday you will see that the question whether this is true or not can be reduced to a question of square function estimate. So this is a first step to see that this question is related to the tools that we did before in the lecture. And then the next 2 weeks, the last 2 weeks of the lectures, will be devoted to prove this square function estimate, so to show that theorem 12.1 is true, the Kato conjecture is true, that indeed for every elliptic coefficient function A, you will have that in the limit case for alpha equal 1/2, things are still okay. So the domain of the square root of L is exactly H1. Okay, that's it for today. Thank you for listening and have a nice week.